So I'm going to introduce some things that I didn't introduce yesterday that I skipped over. And you don't really need them to write Agda, but it is often used a lot. So I thought it was a good idea. Now that I didn't know what to talk about, I thought it was a good idea to introduce it. And so the main one of them is what we call with abstraction. And it's written like this. This is a construct that was first proposed for the programming language Epigram. So Epigram was a programming language that came before Agda, and Agda used a lot of things that were first researched in Epigram. Epigram was very much like a research language, and it didn't really make it as a language. There's not a compiler written in it, but then Agda took some of its features, and one of them is with abstraction. And what it lets you do is it lets you pattern match. So usually we've been pattern matching on the arguments so far, right? So we accept some arguments and then we can pattern match on them. With abstraction, you can add a thing of your own to pattern match. So it doesn't have to be an argument that you have accepted. It can be whatever. So for example, let's say we want to write a filter function. It takes a predicate to Boolean, so for each A, we know whether true or false. It takes a list of A's and it gives back a list of A's such that only the ones for which the predicate gives true are included. If it's the empty list, that's it. Now, if it's the const list, we need to test the element at the top, and there are several ways of doing this. You don't have to use with abstraction. You could just use an if then else, for example. But we can use with abstraction, and then we can pattern match on the result. So we call f, which is the predicate on this x that we get from the list. And so I'll do this slowly. And I'll write this. So at the next line, we have a bar, and we give a variable name to the result of the with call. If you see that is going to be a Boolean. And now I can pattern match on that set the same way I pattern match on normal arguments. And I can give an expression for each of the cases. So in the case it's true, I'm going to include x in the return. And continue to filter recursively. And in the case where it's not true, I'll just skip the x. And there's this alternative notation, which is basically the same, but if you don't want to, you notice that in this case, all of this bit is basically repeated, the same as the line above. So you can use the 3 dots. You don't always want to do that because sometimes pattern matching with a with, so not in this case because it's just true and false, but sometimes pattern matching on the result of the with clause allows you to further inspect the thing on the left. So the types on the thing on the left can change depending on the result of the with. So you don't want to always have the 3 dots, but sometimes, like in this case, you do. And it is more useful than just on this, because it's used as a way of generalizing over the value that you're discriminating over. So let's have a look at that. Let's say we have this theorem that says for any natural numbers n and m, if you have a predicate that holds on the sum of them, n plus m, then it holds for m plus n. And this is obviously true because we proved before that plus is commutative, and it is furthermore true because we showed that we can substitute something in a type. So we had this, I think it was on Monday. We had this proof here, transport, that says if x and y are the same and p holds for x, then p holds for y. And basically here, x is n plus n and y is n plus n. It's basically the same. And so I'm going to show that. And so if we use pattern matching to do this, we use with abstraction, and we call this commutativity lemma that we proved before on n and m. So this gives you a proof EQ that n plus m equals m plus n, right? Now we can use that to generalize the goal. And what do I mean by that? And if we also pattern match on we can do simultaneous pattern matchings, and here I pattern match on two things: on the result of n plus m, and I call that x, and on this commutativity proof, and I call that EQ. And now you'll see that before, in this case where I only pattern matched on the commutativity lemma, I had EQ, the type of EQ was n plus m equals m plus n. But now that I have I used with abstraction on m plus m, you see that this thing here, it's not n plus m anymore. It is this x here, which is the result of that goal. And the same here, p is not true. Before it was p for n plus m, now it is p for x. So we have generalized both the assumptions, and well, in this case, it doesn't appear in the goal, but if it did, also the goal. We have generalized it over the result of this. And what does that allow you to do? What it allows you to do? What I don't do it.
Is there a question?
Yeah.
There is a question.
Oh, sorry. Yeah.
No.
Oh, so we've introduced. Yes. So it introduces a new variable in scope. So in this case, for example, x is a new variable in scope, and furthermore, you can pattern match on that variable, and when you pattern match on that variable, the result will affect both the type of the goal and the type of the assumptions that you have in scope. So it is dependent pattern matching the same way we have been doing it so far on the left-hand side of the inequality, but it allows you to include arbitrary expressions. So you don't have to only pattern match on the arguments, you can pattern match on whatever you like. So now that we have introduced this, we can make some magic happen. When we pattern match on the equality, we get this. And so that has, when we pattern match on the equality, see that before the pattern match, we have that EQ, the type of EQ is x equals m plus n. And when we pattern match on this equality, Agda will substitute in the goal and in the assumptions all the references to x with the other side of the equality, n plus n. So this x here in P of x will become free of n plus n. And another thing that you'll notice is that here we get this dot syntax. And that means that because we have pattern matched on this, and this is reflexivity, and this was a proof that x equals n plus n. What was before x is now determined to be n plus n. So it means that x here can only be one possible thing, and it is going to be n plus n. It has to be this concrete value. And that is the way that Agda has of letting you know that this is uniquely determined. This argument is determined uniquely by another argument. It cannot be anything else but that.
But the dot is something that will appear when pattern matching, but it's not something that you will ever enter.
Correct. You can try sometimes to enter it, because sometimes maybe the pattern matching or you're doing some everything, like you can write it yourself. I think you can, I could create this off as an X, and that would be okay, I think, yes. So you see that here, before we just had x is a natural number. Now we also have x equals n plus n. And so, yeah, that's what the dot pattern does. You can also have it as dot underscore, and that's sometimes useful when it's a like very big expression. And the point is like, well, if it's uniquely determined, then why do I care about this very big expression? It cannot be anything else. So I want to ignore it because it's very verbose. You can just use the underscore. But yeah. And well, this is as before. And now we see that by pattern matching on this m plus m, what was before p of n plus m became p of x, and then by pattern matching on this equality, x became n plus n. So now we have a proof that p on n plus n holds, and that is exactly what we need. So we can say p. And this pattern, this way of doing things, is so common that there's special syntax for it. So this is like a syntactic sugar, basically. And it is a rewrite keyword. So, let's say again that we want to prove the same thing. And we know about this lemma that tells you that m plus n equals m plus n. Then we can use rewrite here on the right, on the left-hand side of the quality to rewrite the type of the assumptions and of the goal by this thing here. And so that's what we get here. Whenever Agda sees in one of the assumptions or in one of the goals, it sees n plus m, it substitutes that, it rewrites that into n plus n. So the types change of the assumptions and of the goal. And so we can just say p. So all these equations that we have been proven so far with like congruence and transitivity and blah, 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 we could have done this using rewrite. And it is in some ways a lot easier to do it using rewrite because you can just say rewrite by this, rewrite by that, and then ruffle and drop done. And that's okay. The only thing is that it's a bit computationally more costly because Agda needs to search, like it needs to go through all the assumptions and all the goals and search where to do the replacement. While, for example, if you were to use, in this case, substitution directly, you would tell it, here is exactly where I want this rewrite to happen. So it's a bit like using a shotgun to kill a fly. So it is sometimes useful if you want to just like get things done quickly. But yeah, if you have big proofs, you don't want to. Also because it's not very, like you don't really see what happens. But it's true. This is very much like the rewrite tactic in Coq or Lin. So there's a tactic that does exactly the same thing. You give it a proof of an equality and it rewrites by that equality in the goal and in the assumptions. This is basically the same thing.
When you have several multiple rewrite rules in the same length.
Yes. So you can have you can do multiple rewrites separating them with this. And that also applies for with. So you can do with multiple things and simultaneous rewrites. So you can also combine rewrites and with as well. Yeah. So like personally, I try to not use it. Sometimes it's like too much of a bother and just like whatever. But yeah. Any questions with that before I jump to the next thing? I went really quickly. I was expecting to take longer. Okay.
I'm sorry, I don't want to drag the.
No, not at all. Like it's too short.
But there's something that I should have understood well on Monday and still haven't, and it's the Rebrackets notation when defining new types.
Yeah. So the curly brace is this one.
Yeah.
Yeah.
But But also in the type definition of the
Yeah,
in the
so
statement of the
yes.
theorem.
So these are implicit arguments. So for example, let's see. Yeah, so we had this proof telling us that about the fact that addition had 0 as the identity on the right. And this proof accepted one argument, which is x, and then it shows you that this was the case. And sometimes, for example, whenever you accept this as part of an interface, like we did with a monoid, you don't want to, you're using it to apply rules and do rewrites, and often you don't want to have this x as part of the type. You don't want to have to specify what x exactly it applies to, because Agda can often deduce it for you. So what you can do is you can make it implicit. And so before, like whenever I wanted to, let's say, okay, let's try this example, and I'm going to show that that 1 plus x plus 0 equals 1 plus x. And I'm going to show that x. And I can here use this proof that we already have, and I will give it, sorry, I will accept first x as an argument, and then I will give it this, right? And that's okay. But Agda can, in fact, figure it out itself because of the shape. It can just like do unification and say, well, it can only be one thing. And so I can use this underscore to have it, to omit having to supply the argument. But sometimes even supplying the underscore is too much, and I just want to say by identity. And we can do that by having x as an implicit argument. So I mark something implicit by using this curly braces notation. And now by default, I won't have, so see that if I don't have it as implicit, the type of the goal will be this. So for all x, this. However, when I have this implicit, instead of for all x, that, and just get that. So there's no for all x anymore, because for all x is implicit. I can still accept it as an argument if I want to. So I can't say here x as an argument, because it's not an explicit argument. But if I want to accept it, I can still use this curly braces notation in the argument position to accept it as an argument. And so, for example, here, I can call the previous identity with that implicit x. Or I can just, well, yeah. And so, for example, the same example. Becomes, yes, sorry. Yeah. So we don't have to pass it an argument anymore. So implicit arguments are arguments that they are provided, you just don't see it really. You can see it if you want it, but if you want it, you can just ignore it. Yeah.
But then in the theorem on the left.
Yeah. So in the theorem on the left, well, it.
No, they're more in like higher up.
This one.
Yeah, that's implicit, but then it's in the. It's there as argument.
Yeah, so this is an uppercase P, and this is a lowercase p computer.
Sure.
So,
yeah, sorry.
Let's try PR for proof and PR. So here I'm not accepting it as an argument. If I wanted to accept it as an argument, then I would have to write this, which is why I do here below.
Thank you.
So for example, I think the reason I need to have it here is that if I don't, if I don't provide a substitution with B as an argument, you'll see that I get this yellow, which means Agda cannot deduce what this implicit argument has to be. So here I need to pass an implicit argument, I need to pass it explicitly. And so I say B. Yeah.
Thank you.
Yeah. Okay. Any other questions so far? Okay. So now I'll briefly talk a bit on co-induction. So far we've seen inductive data types, meaning data types that eventually they have some kind of base case. Now we'll see. So if you do recursion on an inductive data type, you know that eventually you will terminate, right? Because you have a base case. However, there are also co-inductive data types, which are data types that can go on forever. They are potentially infinite. And for example, in Haskell, you have the type of lists, and because Haskell is lazily evaluated, you can have infinite lists using this list data type. But Haskell does not differentiate between infinite lists and finite lists. They are the same data type. So you don't really know by the type whether this thing you're given is going to be potentially infinite or not, right? In Agda, we do distinguish. So inductive data types, they have to be finite. They have to terminate at some point. And co-inductive data types, they don't have to. They always have to produce. So as long as to a co-inductive data type, you can always ask it, so what's the next thing? And it will give it to you. So let's see an example of that. And first the time redefine this. So this, we saw that they are either the empty list or prepending an element to an existing list, right? And you can more or less, or you can abstract over that and provide, let's say, the shape of this. So whenever you want to make a list, you have two choices. You can either make the empty list or you can make a cons, right? When you make the empty list, you don't have to provide anything. That's it, the job is done. Right? When you make a cons, you need to provide two things, the element and the continuation of the list. And this type represents exactly that. So this type accepts two parameters, x, which is the elements of the list, and b, which is the type of the tail of the list. And so if you want to make something of this type, you have two choices. And here is where this or comes in. So you either go left and you supply top, and this model creating the empty list, or you go right and you supply two things, one element of x and the tail of the list. So this type here is the algebra for this type here. It's exactly the same thing. Instead of using two separate constructors, we use the two constructors in sum to differentiate between the two cases. And for the empty constructor, we say top, because top doesn't contain any information, which is exactly what the empty list needs, like it needs no information. And if we choose cons, then we need to provide one element of x, which is the element a, and b, b being the type of the tail of the list. So for example, if we are given something of this type that has an A as an element and a list as a continuation, we can build a normal list. So I'm going to pattern match it. And we have two choices. We have two possible cases. One, the thing went left, and therefore x is top. So when we pattern match against it, we'll get nothing. And in that case, we built the empty list. Or we went right, and we have two things. One is the A, and the other one is the continuation. And so we write A plus X. Does it make sense? Yeah. And so I can generalize.
If you wanted to make, for example, the empty list T, not convert the empty list to the real empty list. If you wanted to make an empty list with type list T, you would use INL.
Yes, you'll say go left, and then you would supply an inhabitant of top, which is DT, and yeah, and that's it. So this is a way of separating. So here we see when we define lists like this, we make it so that all the tables are of this very same type. However, with this list T, we leave open the possibility that the tail is some other type. And we can use this. As an algebra, meaning that if we are given a list T with potentially an element of A, but where the tail has already been processed into some B, and we know how to process that list into a B, then we know how to process a complete list of A's into B's. So this is for Darfur list. So as the first argument, we accept this function that takes a list that is potentially empty and gives you a B, or the list can be inhabited, it can be a cons, and if it is a cons, it will have an A in the head, and something that has already been processed into a B as a tail. So we are saying that if I want to process a list of A's into a B, all I need to know is how to deal with the base case, the empty list, and how to deal with a case where the tail of the list has already been processed, and I want to add the head. So let's go through this. So let's say I have the empty list. I need to return a B. And the only way I can generate a B is by using this algebra. And this algebra takes one argument, and it is something of this type, list T. And there's to make something of type list T, I can either go left and provide TT, or go right and provide an A and a B. In this case, I don't have an A, so I'll have to go left and provide TT. When there is a cons, on the other hand, I'll use the algebra too, but I'm going to go right, and I need to provide two things. I need to provide the element of A, which is cons, which is X, and I need to provide the tail, but it is a requirement that the tail has already been processed into P, and that's where the recursive call comes in. I'm going to process the rest of the list. So this is a way of decoupling the algebra on a type from the recursion, let's say. So for example, I can use that to write the ideal functional list that will just traverse the list and construct another list as the same list as output. So basically that's nothing. And I'm going to use folder, and the algebra I'm going to provide is going to be what did I have here? Oh, yeah, it's going to be this make list. Yeah, fine. I need to describe a way of converting a partially processed list And when I mean a partially processed list is a list where if the list has a tail, that has already been processed. So I need to process a partially processed list into a complete list. And that is exactly what I explained how to do here. So here I have a partially processed list where the tail is already a list. And I process that into a complete list. And so yeah, I use that. We can also use that to write the function length, which computes the length of a list. So I'm going to use folder. And so I need to, given a list, I need to return a natural number. And using folder, the requirement is translated into this, which says that given a list that has the tail already processed into a natural number, I need to process that into a natural number. So it's a list that has been partially processed. I don't know how to explain this better. And I'll use this increment function here. So either the partially processed list is the empty list, in which case I will say 0, or the partially processed list has an element, which I don't care about because I'm just computing the length. And the second element is already the number of things in the table. I'm going to say successor of n. I can use that as algebra. And so that is an algebra list. Now, conductive data types in Agda are introduced as records, and you have to specify that they are conductive here. Otherwise, everything else is the same. The fields, you can have several fields. Here I have only one field, and it's going to give you a partially processed list where the tail is a conductive list itself. So this type this refers to top or an A and a column. So these two things are the same. So these are potentially infinite lists. And whenever I ask for the next element, I'm going to get something in return that is either left and top, which means that is the end of the list, or I'm going to get two things back, which is one more element, and then the rest of the conductive list. And that is how you model potentially infinite lists in Agda. So every time I ask for the next one, I get either nothing, so this left top, or I get one element and the tail of the conductive list. And so they are potentially infinite lists, so we can have the empty list. And when we want to define a conductive data type, we can use this co-pattern matching that we already saw. So here I do Control-C, Control-C space, and you'll see that we get the next field on the left-hand side. And so I will have to specify what to return for that. And so because I want to model the empty list, I'm going to say in left CT. So I'm going to return this guy here. However, if I want to prepend something to something that is already a conductive list, I'm going to do CC again. I get next on the left hand side, and I say go right, and I give two things, X and XS. And with that, I can write unfolder. The folder took a list and munched things together, brushed things together to give you one result as the result here. Folder takes a list and a way of converting A's and already partially constructed B's into B's, and it gives you back a B. So it's an algebra list. This is a coalgebra list, so it will accept a seed. So this is like a pseudo-random number generator, let's say. It accepts a seed and gives you pseudo number, random number, and the next seed, let's say, and this is basically the same idea. So this thing, it accepts a algebra, which is a function that goes from a seed to a potentially empty list that has an A and another seed. And given an initial seed, it constructs a potentially infinite list. So here is where we start using with abstraction. So we call the coalgebra on the initial seed that we have. Coalgebra here accepts an S, and we have an S, so we apply it. So we do with coalgebra on S. And we have two possibilities. Either before that, need to construct a goal list and then to pattern match on the return type. So I get a co-pattern, and then I do S. I have two possibilities. Either the coalgebra returns the empty list, in which case the goal list I need to construct is just the empty list as well, or it returns two things, an A and the new seed. And in that case, I'm going to go right, I'm going to provide the A and recursively call the unfolder with the same coalgebra, but with a new seed. So this unfolding, so it accepts a function that goes from a seed to a list that is either maybe the empty list, or it is a cons with one element and the continuation seed as a tail. It accepts an initial seed, and it constructs this co-inductive lists with those elements. It will basically keep calling this function on the new seeds until it gets nothing, this in left dt, in which case it stops. And we can use that for example, to generate an infinite list that just repeats the same element over and over again. And how do we do that? Well, we start with a seed, which is the element that we want to repeat. And each time we are asked for the next element, we will return this element. And we will also say that this same element is going to be the next seed. So we insert A as the argument, and pattern match on the result so that we get next to the left. And then we always go right. We provide A as the element, and we provide A. We provide A as the next seed. In fact, sorry, I think we can here we don't have to construct it this way. We can just use unfolder, which is the point, actually. When I'm given a seed, I'm going to return that seed as the element, and I'm also going to return it. The seed as the element, and I'm also going to return it as the next seed. And so these are potentially infinite lists, and we can convert them into lists, but we can convert them only up to a finite point. So I'm going to accept as an argument how many elements to take, and I'm going to get elements from the call list until I get to 0 and return them as a finite list. So if I'm asked for 0 elements, well, then I'm just going to return the empty list. If I'm asked for at least one element, I will see what's the next. I will force the conductive type, ask for the next element of it, and I'm either returned nothing, in which case, even if I'm asked for, let's say, 5 elements, and if the call list only returns 3, well, then that's it. I'll have to return the empty list. However, if it does return something, I'm going to return that something and continue processing. And so call lists are potentially infinite lists, but they can be empty. You can also model lists that have to be infinite, that can only be infinite, they will never end, and those are called streams. Before we had this type here for call lists, so it was either the empty list or it was one element and the continuation. Now it is just that one element and the continuation. There's no possibility for the empty case. So this thing with 2 constructors is exactly the same as this thing, which is kind of like what we had before. Before we had the possibility that it is empty. Now we don't. And so I have it as 2 fields, the head of the stream and the tail of the stream. And so we can define forever x as a stream that forever returns x, for example. So we say the head of forever x is going to be x, and the tail of forever x is going to be forever x. And we can also do this with the same principle that we used for unfolding call lists, which is start from a seed and then build according to that seed, returning a continuation seed. We can do the same thing here as well. So we are given a algebra that from a seed returns an element and a new seed. We are given an initial seed, and we are going to construct a stream with it. So we start by pattern matching. And the result is to return 2 things, an A and the new seed. And this pattern matching answer. So the head of a algebra on S is just going to be first of call S. I'm going to call the algebra on this seed and take this A from the return type, so that's why I use first. And the tail of it is going to be second of algebra of S or not. For the tail case, I first get the continuation seed and then feed that into the unfold. Yeah. And unless there's any other questions, I guess that's, yeah.
I have a question. Yeah. Or let's say, can it pose a challenge?
Yeah.
Could you prove, for example, that every natural number can be decomposed in prime numbers? Do we have that?
Yeah.
Could we try, for example? Or is it very hard?
I mean, I would probably need your help to how to state the theorem in the first place.
Given a natural number,
Yeah.
you can write it into a prime decomposition.
Yes. Yeah, I guess we would first need to characterize what a prime number is. Yes. Can I get back at you on that though? I want to do it in real time. I think it should be doable.
I see. So yes, I guess it's harder to do it in real time. Just because you have to sit down, I think.
Mostly because I have to think about how to represent things.
I see.
Yeah. I'll try to get back. So I had some pointers at the end and the documentation for Agda. And this is a pretty complete book, which is also in Chinese and on programming language foundations in Agda. Not that people here do any of that, but and then there's a standard library for Agda, which I showed yesterday to the people in the talk, but I just don't show it here as well. So this is, as you see, this is all clickable HTML. So you can have Agda generate files with a source code, and those files are in HTML, and you can click it and go to the definition. So everything is clickable, which is really nice. It's really easy to navigate. And yeah, there's lots of common things. So what people use most is when you have algebras, category theory stuff for data. Then you have the main one, which is data types, which is what people use the most. We have containers.
Do you have number theory here?
I don't think so. No. And so it's not so much a library of theories. It's more a library of tools or usual definitions. Not so much. So you have some proofs around it, but it's not anything major. Yeah. But yeah, there's a lot of useful stuff. So usually, most of the things we defined are already defined in the standard library. It wasn't defined in the standard. And then I guess I could, even though there's plenty of time, I could show the kind of things we use or I use Agda for, which is to define programming languages. So in a programming language, you usually, well, it depends, but you can approach it in a way which is you define first the syntax for the programming language. So this is what the syntactic reality of it, and then you define types for that programming language, and then you define a typing judgment, which is some a logical system where you define if this is one type with this type, this syntax is one type with this type, this expression has this type, then if you put them together using this operator, you'll get this type. And so that way you rule out programs that are not correctly typed, for example. And this is an example of how it looks. So this is a judgment. So this is a data type that models a logical judgment. It has 3 elements. On the left-hand side of the entails, you have the typing context. So typing context is an association of variables with types. And then on the right-hand side of the entails and before the column, you have the expression that you're typing. So first of something or in left or in right, whatever. And then on the right-hand side of the column, you have the type of that expression. So for example, here I say that under any typing environment, so there's no requirement in the typing environment, top is of type top, TT is of type top. Or that if you have under typing environment an expression which is of some product type, if you do it first of that expression, then you will get the type on the left. Or the opposite, if you have E that is of a product type and you do second of E, you will get the type on the right. And yeah, those are some examples of that. In this case, this is the first step to defining a type system for the pi calculus, which is a calculus for concurrency. And this is with shared types. So shared types are things that you can use as much as you like. So that's what we are used to in programming languages. So if you have a variable, you can refer to it as much as you like. And what we work on most of the time is linear type systems. So this is type systems where you can use each variable exactly once. And so you have on each variable, you have usage annotations that tell you how many times you have used that. So in the typing context, it's not just like an association of variables with types, it has also usage information in them. And so you need to carefully split things and add things up to preserve some properties. And what you usually do is you first model this, and well, if you're not familiar with it, on pen and paper, these kind of rules are presented very much like this. So this would look like something like gamma tells B, and gamma tells Q, then gamma tells compose Q. It looks pretty similar to what we have here. So if you add basically a line there, which you can also do because it's a comment, it's pretty much the same thing. Which is nice. So yeah, we first model, we specify what the type system, we first specify what the syntax is, then we specify what the type system is. We often give to the syntax, we give it an operational semantics, so how it behaves when you run the program, what happens. And then you do things like prove that, well, if you start with a program that is well typed under this context, and you run the program, you will arrive to a new program that is also well typed under this context. And that's, you do some proofs to show that that is the case. And yeah, in programming languages, like things like formalizations they are really useful because even if the reasoning behind why something, for example, preserves the typing judgment, maybe the reasoning is not complicated, but there's like lots of cases and lots of things that if you're not careful to check, yeah, things might go wrong. So it's something that prevents you from fucking up, basically. Yeah.
Can you model or formalize like an overflow, stack overflow?
Yeah, we don't do that, but I think there's things that formalizations that try to model memory management, and maybe those like maybe in those cases you want to prove that that will never happen, for example. Yeah. Yeah. Like there's a whole bunch of different fields in this field, like as a subfield. Yeah. And that's everything I have to show.